In this lecture, we look at heat. Heat is the energy transferred between a system and its environment due to a temperature difference between the system and the environment. Here we show the environment as the background green, and the system is the light blue rectangle. The temperature of the environment is T sub E, the temperature of the system is T sub S. If the temperature of the environment is greater than the temperature of the system, heat, symbolized by Q, flows into the system from the environment. If the temperature of the environment is less than the temperature of the system, heat flows from the system into the environment. Of course, if the system and the environment have the same temperature, then no heat flows because they are in thermal equilibrium. Mathematically, the heat is equal to capital C times delta T, the change in temperature, where capital C is the heat capacity of an object, and it determines how much a given amount of heat changes the temperature of the object. So its units are joules per degree K. Or we can write the heat in terms of little c, which is the specific heat of a particular material, times the mass of material, times the change in temperature. Little c is, of course, then equal to the heat capacity divided by the mass. Here's a table of specific heats for copper, aluminum, glass, and water. You can see there are some rather strong variations, copper having the smallest and water having a value that's more than a factor of 10 larger. How much heat is required to raise a 10 kilogram block of copper by 10 degrees K? Well, Q is equal to C sub copper times the mass times delta T. So there's 10 kilograms of copper times a change of 10 K, so that's 100 times the specific heat. So 100 times 386 is 38,600 joules. What if we were to do this for 10 kilograms of water? Well, then Q is equal to the specific heat of water, which is 4,190 times 10 times 10, or times 100, which is 419,000 joules. It is important to know that the specific heats depend on temperature, pressure, and volume. So these are values at room temperature, but they hold true if you don't get too far away from room temperature. Let's look at phase changes and heats of transformation. The heat of vaporization is the joules per, the energy per mass added to change liquid to a vapor, and that's symbolized by L sub V. So if we have heat being applied to some fluid, which is turning it into a vapor, then the heat required to turn all the fluid into the vapor is equal to the mass of fluid times this quantity L sub V. So the heat of vaporization. The heat of fusion required to change liquid to a solid is symbolized by L sub F. So if we have a refrigerator and we're cooling down a fluid till it freezes, then the heat removed from the fluid is given by minus times the mass of the fluid times this heat of fusion. So let's take an example from if we take ice and turn it into steam. How much heat must be added to turn 1 kilogram of ice at minus 10 degrees C to steam at 100 degrees C? Well, we first need, in our first step, we have to take and warm up the ice to the melting point at 0 degrees C. And then in the next step, we have to turn the solid ice to water, so we need the heat of fusion for water. Then we need to warm up the water, so we need the specific heat of water. And finally, we need to vaporize the water, so we need the heat of vaporization of water, which is given there. First step, we want to raise the temperature of the ice by 10 degrees C. So Q1 is equal to the C of the ice times the mass times delta T. Well, we have this is just basically multiplying by a factor of 10 because we're changing the temperature by 10 degrees. So we go from 2,220 to 22,200 joules. Then we need to transform days to water, and that's equal to Q2 is equal to the mass of the water times the heat of fusion. So that's, we take 333 kilojoules times the heat of times the mass, which is 1 kilogram, so it's 333,000 joules. Then we need to raise the temperature of the water by 100 degrees C to get to the point at which it starts to boil. And Q3 then is equal to the specific heat of water times the mass times the change in temperature. And we plug in those numbers, we get 419,000 joules. And last, we need to transform the water to steam. And then that's equal to the mass times the heat of vaporization. And that's equal to 2,256,000 joules. If we add all those up, then the total heat needed to do this is 3,030,200 joules. You can see one of the largest amount is turning the water into vapor.